Hello, everyone. Welcome to my talk. I'm Chris Lehnert. I'm from the QUT Centre for Robotics here in Brisbane, Australia. And today I'll be talking to you about using active robotic vision technique to deal with visual occlusions in robotic harvesting for the DigiCop Conference 2020. So one of the biggest challenges in horticulture, which is a very large industry in Australia, is over $2.4 billion annually. And similarly, in the US, it's at least 18 billion. One of the biggest challenges is labor cost and labor accessibility. And on average, in horticulture, the cost of production is around 20 to 30%, but can vary wildly depending on the climate and situations in each country. One of the challenges that we've been looking at is the ability to use robotics and technology to assist and autonomously harvest sweet peppers or any crop in this industry. As you can see in this video, it can be a very complex and dexterous manipulation task to have to remove the fruit from the plant. And one thing I want to highlight is that it's very occlusive. So all of the leaves and branches can block the visual perspective of the fruit in the plant. And this is one thing that we're going to look at addressing using active vision techniques. Here at QUT, in the past, we've developed a sweet pepper harvesting robot called Harvey, where we've been looking at using deep learning techniques to identify a cutting position on the sweet pepper and autonomously use a harvesting tool to grasp and cut free the sweet peppers from the plant. And we've shown some impressive performances of this robot, which we can reach around 76% of removing fruit from the plant in real protected cropping field trials. But what we noticed was our performance was related to how we could see the fruit within the plant. So we've since then been looking at how do we use active vision or being able to move the camera in the space to see the fruit better and therefore improve our performance on removing fruit from the plant. So here's one way that we've approached it in the past, where we've been looking at doing scanning techniques. But one thing I wanted to highlight here is that this takes costly time into consideration. So we might be wasting more time than necessary to scan the environment and get a better view of the fruit. In this particular example, I'm not showing one that's also occluded, but based from leaves. We tried a few different patterns, but one thing we wanted to approach, which was deciding on how can we come up with methods that can decide the most optimal trajectory to move the camera to improve the view of the fruit. And as I said before, some of the challenges in this type of domain is that we've got highly occluded fruit from the natural leaf, and we've got variation in the structure and shape of the fruit, which means we can't use traditional visual servoing techniques if we are looking at trying to improve the view for cutting or doing a specific task like harvesting. So one of the proposed solutions that we've come up with is being able to use multiple perspectives at any instant in time using a specially designed 3D multi-camera array tool, which we place on the end effector of a robotic arm and use the information that it generates to choose the next best motion that will improve the view of the fruit. Now, this allows the system to be able to choose which path in 3D space and what rotation will get the best view over time. And we're also looking at, this is trying to approach the problem where we're minimizing the amount of time needed to move through the space, which in most instances, harvesting time is cost for harvesting. The camera that we decided on using, we had to design ourselves within our lab. We used, to rapidly prototype this system, we used 3D printing and a cluster of Raspberry Pi computers, all connected to 9 separate Pi cameras. What I wanted to note here, though, is that we've specially designed the position of the cameras to get not just different perspectives in a 2D plane, but also stepwise in 3 dimensions as well. And therefore, we called it 3D move to C. The experimental setup we used was inside our lab, where we used an artificial plant with very realistic looking leaves and fruit. And we set up different cameras and diffused light to look at the effect of different lighting conditions on this platform. And we used our harvesting platform, Harvey, to look at how we can use the 7 degrees of freedom that the platform has to move around the space with the new Move to See camera. So this is our proposed method. And as you can see here, this is with this experiment, we were only able to slowly move the camera, and that was due to limitations with the hardware in streaming the camera images to the desktop computer. But what you can see here is examples of it from different initial conditions and different occlusion conditions. The camera is able to move through its environment and pick the best next view to therefore maximize its view at the end condition. And in order to get a comparison of this method, we used a standard RGBD camera and did a single point-to-point motion based on the depth image. And you can see when we compare the two in this slide, you find that with our proposed method, we get very consistent end conditions. You can see on the very last right column here, the fruit is in most cases has been maximized its view. We can see the fruit from a highly occluded initial condition, but the RGBD camera, which is in the left-hand columns here, the baseline start and baseline end, we get poor reconstruction, or we don't find a good final image of the fruit. We have been also testing further ideas of how can we use novel deep learning methods to improve and or reduce the limitation with the number of cameras. That was one of the drawbacks of this method, is having to have 9 cameras on a final tool, which can be costly and complex in hardware. So one of our newest methods we've been using is using a deep learning DCNN method to reduce the reliance on having 9 cameras. And what we did was we used the data captured from the multiple cameras as a training method, and then only train the deep learning method to estimate the motion to take from a single image. So therefore, the deep learning system is actually learning from a single perspective where should the end effector be moved so that it improves its view over time. And what you can see here is this actually, even though it's got 9 cameras on it, we are only using 1 camera in this trial, in this video here. And what we see is an almost identical trajectory that sees the fruit, even though it's just using 1 image. It's estimating from the deep network the best optimal trajectory to move to see the fruit. And what we've done here is actually we've done a comparison. So now what we've taken the previous 3D move to see method, and we've compared it to our single image deep network method. We call these deep 3D MTS. And what we see here is almost a identical result from the same starting conditions. The deep network is able to efficiently calculate the motion to maximize the view of the fruit. And that's the results here. In the chart, you can see there's a comparison from the dotted line to the solid line, that using the 3D, using all 9 cameras versus only using a single camera. So this is we think this is a very effective method to be able to use to move a camera through the workspace of the robot to effectively find fruit, even though if it's highly occluded, while also minimizing the amount of time needed to scan through the environment. So what we're also considering for future work in this active vision method is to look at using alternative joint motion updates. So we use a intensive computational inverse kinematics step, and we're thinking about new ways of being able to use just force, fork, or Jacobian, not inverse Jacobian methods. The other thing is to look at novel deep learning techniques like using attention-based methods to improve the generalization of this to new environments, but also looking at ways to combine the segmentation and the estimation of the motion in the deep training network. So one of these things we're also looking at is not only just minimizing what we call the objective function, which is the number of pixels of the fruit, looking at alternative cost functions or objectives, which is looking at, well, how well do we do peduncle estimation, or how well do we grasp, or how well do we actually perform a harvesting after we move that that end effector, and we could potentially feed that back into the training method. So what I'd like to do is I'd like to thank the team that was involved in this project, including the harvesting and the 3D Move to C team. And this work was supported by the Queensland Government and a program called Strategic Investment in Farm Robotics. And I am from the QUT Centre for Robotics. Thank you.